Alright, Crewton Ramone's House of Math, addition and subtraction, and a little problem solving, using manipulatives. Alright, these are million-dollar ideas right here. I was just talking to a teacher recently, and she has a daughter who has a degree in finance, minor in mathematics, went through 12 years of high school and some college, and never got this very simple concept that I'm about to share with you right now explained to her. And she went, wow, I've never seen that before. And teachers, parents, all kinds of people. Alright, the concept is, well, let's back up before I get to that. Numbers are made up of other numbers. I can make a 5 with a 2 and a 3. And I can see that 7 wants to be 10. That's your next concept, is that all the numbers want to be 10. 7 and 3 makes 10, and there'll be 2 left over because that's a 5. But let's say I'm doing a different problem. Here is 12 minus 7. Because all this is 7 plus what is going to be 12? Well, we can see it's 5, and the way we do that is subtract 7 from both sides. We can see that 7 plus 5 is 12, which is the same thing as 5 plus 7, associative property. We can see that 7 and a 5 is made up of other numbers, 3 and a 2. That gives the 7 the 3 that it wants. So 7 plus 3, that's a 10. All right, I'll explain it in symbols. And 2 more, that's 12. Or, let's say the kid doesn't go left to right. He goes right to left. 5, well, then the 5 takes the 5 out of that 7. Can you see that there's a 5 in there? Well, of course you can. And how much more? 2 more. See it? But we want these guys to go together. And then 2 this way, and we'll just go the opposite way. Oops, get on there. Alright, fine, be like that. It's humorous. Because I'm trying to do so many things at once. Alright, hold the camera. Keep it still. Alright, so, can you see it now? The 5 and the 5 makes my 10, and 2 more, 12. Alright. And then we could go the other way. 5 plus what is the same thing as 12? Get rid of all of that and just make that an X. Get rid of all of that, make that an X. Right? And that's how they'll figure it out, is, well, 3 and 2 more. Okay, but what if we're doing subtraction? This is important. So you see how it all goes together using manipulatives? We get addition, subtraction, and problem solving all in one shot, and they can see it, and the subconscious mind sees it, and then when you bring it back out with symbols, it's easy for them to understand. Okay, so here, using the same problem, let's talk about, I want to have a simple problem where I take 12, and we take away 7. Now, people, they're just amazed when I say this. All right, so 12, I'll set it up this way too. 12, and I'm going to take away 7. Well, can I take it out of here? And what the little kids will tell you is, no, talk to the 10. You have to talk to the 10. There's another concept. So basic concepts we've covered. Numbers are made up of other numbers. All the numbers want to be 10. And numbers are made up of, then that when you do subtraction, if you don't have enough, you got to talk to the 10. And again, we're still just doing add-ins. So I can't take it out of this 2, so I do that. And I have, right, so I'm taking this away. The 7 is what I'm taking away. So I've used that to symbolize my taking away. I took it away, it's out of there. So I just add 3. So instead of counting backward, I just add 3, and I get 5. Add the add-in. See how it works? Simple, easy. Makes it really easy for kids to understand what's going on there. And they see the same blocks. And this is all it is. When you get right down to it, this is all it is. And it's hard to explain in a static textbook without with just pencil and paper or just words. You need some video to make this absolutely clear. All I'm saying is, instead of taking and doing this, where I count backwards from 12, all we're going to do is do that. And then I just add the 3 and 2 more to see that I have 5 there. And I can make the final trade. There it is. What did I do? I just took 7 away from 12 in a way that kids can understand. 12 minus 7 is the same thing as 3 plus 2, which is the same thing as 5. Where'd the 3 come from? Because I took the 7 out of that 10. There, you can see it, right? Plain as day. There it is. And then there's 2 more left. So there's my 5. See that? Okay, that's all it is. Very basic concept. But it gives them an algorithm for doing all kinds of math. Making numbers out of other numbers, being able to make make change, add numbers together, and do some problem solving. It's all in there. So now if I look at this and I just write it a slightly different way, same exact blocks, and they'll get it, and they'll understand that, look, I want 7 plus something is the same thing as 12. Or I could say 12 minus something is the same thing as 5. How do we figure this out? Well, the first one's really easy. 7 and some more. So I take the 7 from both sides, and I can set this up as equal. Because a lot of kids look at this and they say that this, and this is the answer. Well, this and this are same. Crucially important concept. Here's another concept. Sameness. Okay, what's on this side is the same as what's on this side. So I have 7, and I'm going to use this as my x, is the same thing, and I'm going to get equal sign, equals, nice equal sign, equals 12. Well, what do I have to do to figure out what this is? Well, is there same on both sides? There sure is same on both sides. Can't see it readily, but now I can. Oh, look, no problem. Oh, so I'll put these guys together over here, because now I can see same. I'll put that like that, see same. Oh, take that, X must be 5. What do? We subtracted 7 from both sides. Right? And the balancing equation is damaging kids. Alright, so now I say 12, I've got 12, and I'm going to take away something, and that's going to be the same thing as 5. Oh, how am I going to, oops, and that's supposed to be an X. How am I going to show that using the blocks? Well, we're using manipulatives, base 10 blocks. Well, let's see here. Let me set it up. Let me set this up nicely. Here and here. Alright. Do we see same on both sides? Well, first thing, I have, oh wait, let me put some symbols down here. Here's my 12, and I'm going to take away something, and that's going to be the same thing as 5. Alright. So what do I do? Well, here a 0 could come in handy. We could take a look and see, do we see same stuff on both sides? I don't see a lot of same stuff on both sides. If I use my same stuff on both sides rule is going to be, or idea, this is going to be tricky, because then I could say, okay, well, yeah, there's a 10 over there. But now I take away stuff that's same, and I'm kind of, okay, now it says 7 minus x is the same thing as 0. Oh, that's pretty simple. 7 minus x is the same thing as 0. They might get it right there. They know that it's got to be 7. But let's go further. And let's just, see, because most of it, they just follow the rules, and you take away 12 and then change this, multiply by 9. How about if I do this? Same. Is there a 0 over here? Yes, there's a 0. So here I'm going to have 0. I'm going to use hero 0 in the form of x. Okay, pay attention. Again, this is going to be an x, and then you know what? I'm going to use this as a negative x because I don't tend to use hollow bars. And do I have one handy? I don't, so I'm just going to do this. I'm going to put a mark on this one so I know. See that right there? See that mark right there? That tells me it's a negative x. That's an ohmi x. An ohmi x and a positive x is the same thing as 0. And we can explain the concept of 0. If I have 5 and I owe 5, that's a 0 right there. And a fancy way of saying 0. So I could do the same thing with anything, any numbers. Have x, owe an x. Let's see here. Well, I've got a negative x here, I owe x, I have an ox, and I have ox. Take these two guys away. They're the same. And now it says x equals 7. And knowing that it's equal, I could put it this way. I could x equals 7. Did I change anything? Little kids will tell you, no, I didn't change anything. But instead of just doing subtract, so because they have this thing with, well, when the x walks across the equal sign, it becomes positive. Nobody's walking across the equal sign. We're using the concept of same. Okay, and using base 10 blocks to solve and show this. All right, let's do other problems where we don't just have 5 and 7 and 12. Okay, algorithms using addition. Right? Okay, so numbers are made up of other numbers, and this is why we spend so much time, and you'll see it on other pages, about building all 45 addends. And then they can see that, let's just quickly, they can see that 5 needs a twin if he's going to be 10. And that those guys are same. And in fact, they might even see the equal sign if you look carefully. Okay, what's another combination? I'm going the other way. 6 and a 4. And this is also in the Curious Counters Compendium. What's next? Oh, a 3. See, there's our friend. Okay. What's left? 2 and 8. And kids will see the pattern. Oh, one less, one more, one less, one more. And last but not least. Okay. Build lots of these. Build all 45 atoms. I'm just doing this to show very quickly in case this is the first time you've ever seen it. We're making numbers out of other numbers. And then all these numbers want to be 10s. And I just did this with a bunch of first graders where they start seeing, it's great, 7 plus 3 is 10. 70 plus how many is going to be 10 tens, 10 tens, 100. And they're much, 40, I don't know, 30. How about 700 plus how many is going to be 1,000? But it's still just 10. And we're still just playing around with 10. See the 10s? And they can see the patterning. Oh, then it must be 300. And one little girl asked, I don't see the pattern. 7 and 3, 7 and 3, it's all the same. There's no pattern. Well, the pattern is more zeros. 7, no 0, now a 0. Oh, how about, kids love big numbers. Makes them excited. Oh, there it is. 10. But now we're talking about thousands. How easy is this stuff? Okay. But then you have to explain it to them. You have to show it to them. You have to use many examples. And you know what? And the question was asked because they're little kids. Will that work with 6 and 4? Don't you love whiteboards? 6 and 4? 60 and 4? My goodness. 60. Oh, there's a pattern. There definitely is. It works every time. Oops, I put the 4 in the wrong place. 4. This is amazing to little kids. It's no big deal to you, but it's amazing. You have to explain it to them and show them. Want to be a 10. Numbers are made up of other numbers. And then we can start getting tricky where we say, okay, 63 needs how much to be 100? There's another exercise that is you're working up the ladder and playing around. Okay. So now, let's say I have numbers that don't add up nicely to 10. Because 8 and 2, well, that's easy. 8 and 2 is 10. That's simple. But what if I had 8 and 7? Well, 8 and 7, and see, when you first work with kids, just play with the manipulatives. They don't need the symbols. 8 and 7, how much is that? Well, I can look at this either way. I can look at this that, using my slider bar here now, I'm going to use this. 8 takes the 2, see the 2? Put it in there. Can you see the 2? Takes the 2, and I'd have 5 left. Or I slide it over this way. Maybe they like the 7 and 3 combination better. 7 takes the 3, 5 left. Either way, I get, I'm just going to write it like this because we write left to right, a 10 and 5, which is, of course, 15. We have a name for it. And there's my equal sign. See the equal, same? See it? The 2 lines? That's where that symbol comes from. We've gotten to the point where parents don't even know where the symbols come from or what they mean or how we came to them. All right. So of course they can't teach, algebra and calculus, or even simple things like, fractions. I had a parent admit to me that she forgot how to do fractions. Okay, so can you see the subtraction in here now is inherent? We can see now if I have these 3 things, and then they talk about pyramids, right? And I've seen guys, they make a big deal out of using the pyramid, where I have 15 and a 7 and an 8, and it's like a magic triangle where if I take 15 minus 8, I'm going to get 7. And if I take 15 minus 7, I'm going to get 8. And if I take 7 plus 8, I'm going to get 15. Right? All we're looking at is this. Of course. Simple and easy. No magic to it. Visually obvious. All right. Now, if I have 15 again, and I want to subtract 8, 15 take away 8. Well, see, don't count backwards. Don't use your slider thing and count backwards. Just move this over, and you can see it's 2 and 5. So I just add the 2, get 7. And I can put a little plus 2 there. You see the 2? No. And 5 more, that's a 7. There's a 7 there. Right? But rather than just 2 and 5, do the small addition instead to get your 7. Because I take that 8 out of one of those 10s. And then you can show them, oh look, what if it's 25? Now the 15's, that's it, 25. Now the 15's hiding. So I get 2 10s. But you can still see it there. And I could line it up like that if I wanted to. And then just take it out of one of these 10s, and I still go, what am I going to get now? Well, there's an extra 10, there's a 2. There's my 10. And a lot of times we just mark like that so we can remember. And 35. And they'll see that, oh, it's the same problem. Just add another 10, and all I got to do is talk to one of the 10s when I do this. Because they get confused. 3, I can't take the 8 out of the 3. No, we're talking about 10s there. So can you see the 15? Now you can see the 15 very clearly, and people will get confused and use this and do the borrowing thing to try and show that that's a 2. But rather than do that and get confused and have more, break the rules and have more than 110, or excuse me, 9 units in the ones place, let's just keep to the rules, be consistent, and say, look, I'm going to take it out of one of these 10s. So I just cross that. I know it's a 2. I add my 2. Add my 2. Yeah. So I add the 2, get 7, and there's 1 left. 1 less, 10 left. So I have only 2 10s there. And they can see it. It's visually obvious. And I can do it this way if I want to do it. You know, people don't get caught up in the model where you're stuck because you have to, right? Okay. Because, you know, they got to show that, you know, I must have it like this. And 1, 2, 3, 4, 5. Oops, 6. And then I got to take away a negative, and I'm going to put it underneath so it shows exactly the same way as the symbol. Great, you can do that, but they get it. Okay. And then, what if it was 18 now? Do I even need blocks? I know my talk to the 10 thing. I can see that, and I'm going to just add 2 to get the 7, and now that's going to be 1 less, because 2 minus. That's easy. Right, there won't be block dependent. And again, this is, you know, we're marching up very quickly because I'm making a video. You do this over weeks and months. Right? Get very comfortable building with blocks. Get very comfortable playing and having a good time and making numbers out of other numbers and all 45 add-ins and making towers and playing what's under the cup. Where's my cup? The old cup that I had that I found. Let's see here. So, what's under the cup? And I'm going to try and show you so you can see what's under the cup. All right, so we got this big tall cup. I've got a 10 there, and I'm going to have, I'll do it so you can see, 5 under the cup, and I want to make 10 and 5 showing. What has to be under the cup? It has to be a 5. Kids love that game. What did we just figure out? 5 plus x is the same thing as a 10. The cup tells you it has to be 5. Right? And then one day, you can lift up the cup and have an X under there and say, oh, we don't need the cup anymore. We'll just always use the X. But it's not as much fun using the X. Right? But that way they can never cheat and they can never peek because we have the X for the cup. And kids understand that, and it's easy. No concept beyond the grasp of a child if it's presented at the child level. Play games. Have fun. Tons of links on the blog and on this website about different games you can use to teach addition and subtraction. And can you see how they go together? They're inverse functions, and you can't talk about addition without subtraction. You can't talk about subtraction without addition. And of course, problem solving comes along for the ride in algebra and so forth. Okay, don't just use them for simple addition and maybe some place value and some subtraction. You can use these for so much more. This is just the very beginning. So, addition, subtraction, and problem solving using manipulatives. All right. Crewton Ramone's House of Math.com
4 more.